Hello, this is Brandon McCullum. In this video, I will be going into more depth on this isopropanol synthesis, right? And I will be taking a material balance of each of these three, right? The reactor, the distillation, and azeotropic distillation. So if we look at our code from part B here, we already have an overall mass balance, right? So I'm going to add a code here, and I will create a second set of equations. And this first part is going to be similar to before. I'm going to now change this to reactor feed and reactor product, because we're now dealing with the distillation and azeotropic distillation as well. So now if we look at our reactor feed, right, we have our alkene feed and our water feed, as well as this recycled water. Some of that water is recycled from our distillation column, right? So I will call that D1 D bottom, right? So D1 bottom times D1 bottom mole fractions. And then we also have our decanter water from the azeotropic distillation, right? So D dot decanter W times D dot decanter WX. The reactions will work the same way, but this product here, right? I don't want the ether and alcohol product. Now I want just this distillation, right? So I will call this distillation feed. Right? So D dot distillation feed times D dot distillation feed X. And I no longer want to return just this. I want to call this reactor balance, and we will return this in an array later on. And then of course change this to reactor feed and reactor products. Okay. So now moving on, if we look at our next column here, right, we have our distillation. We want to look at the mass balance. So we have our feed going in, distillation balance. Oops. And we have our D dot D1 feed times D dot D1 feed X, right? And coming out of here, did I miss an L? Yeah. Coming out of here, we have our bottom and our top. Right, so I will use this this bottom here. Then I will use D1D, right? So that's our distillate, D1 distillate for the top there, D1DX, right? And let me shorten this. Just dist balance. And then now what I want to do is I want to look at the equilibrium within this distillation, right? So everything that comes out of the top, everything that's distilled is going to be a vapor, and everything that comes out the bottom is going to be liquid, right? So we actually have a vapor-liquid equilibrium here. So distillation VLE equals D dot D1 dy, right? I want to change this to y because it is a vapor, over D dot D1bx. And we want to subtract our equilibrium constant K. Now we can move on to this azeotropic distillation. So we have AZ balance, and coming in we have our distillate, right? So that's this D1D, and coming out we have our decanter water, as well as our ether and our alcohol products. So minus d dot ether P times d dot ether X minus d dot alcohol P times d dot alcohol X. All right. Now, one last thing I want to look at here is this alkene to water or water to alkene ratio. Right? So before we just used the water and the alkene flow, but now we also have this recycle here. So we want to add in a constraint here so that we know the ratio of water to alkene. So I'm going to call that the Warfer constraint. And so what Warfer stands for is water to alkene reactor feed ratio. Right? So we're going to take all of our water inputs, so our decanter, plus our, I guess I could have done those together, but our distillate bottom output, plus our water feed. And I want to go ahead and remove these mole fractions here, right? Because we are talking about the flow and not the contents. And then we want to divide by our propylene flow, right? And then we want to subtract our water to alkene reactor feed ratio. And we will return this. So in order to put all of these together, right, I can concatenate all of these vectors using NumPy, but because this warfare constraint is not a vector, it's a single value, I also need to import JAX. So import jax.numpy as JNP. Missed a space here. All right, sure that works. And now I can say jnp.concatenate with our reactor balance. Oh, and I need to put these in brackets. Our distillation balance, our distillation vapor liquid equilibrium, and our azeotropic distillation balance. And then for this warfare constraint, I need to do jnp dot at least 1d and then put it inside those parentheses. And what that does is it actually turns it into a vector. All right. So now I have all of my equations within this. So now I'm going to go ahead and add in my variables. So if we look, we have four equations that use our vector of 4 components, right? So that will be 16 total equations plus 1 equation for this water to alkene reactor feed ratio. And that brings us to a total of 17 equations, which means that we can have 17 unknowns, which I will go ahead and write in now, along with our other known variables that we can measure. All right, so now if we go ahead and look in here, we have the flow feed of water and recycle water is 12 times the alkene flow rate. That's going to be our water to alkene reactor feed ratio. So that equals 12, and I'm going to write that out here. Water alkene reactor feed ratio. Right. Next, we have our azeotropic decanter water, right? And our mole fractions for that. Right? and that is going to be an array, and it's going to be a very small amount of alkene, a little bit of our ether, a little bit of alcohol, and then mostly water, right? And this value actually in here is wrong. That's what we're going to be using for one of our guesses for an unknown later, right? So now we have our mole fraction ratio, right? So that's our that's going to be in our vapor liquid equilibrium for our distillation. So that's D1K. That's an array. All right. And now we need to go ahead and put in our unknown variables. And I'm actually going to move this up next to Warfare here, right? So that our unknown and known variables are a little bit more separate. So we start off with our decanter water flow, and that is going to be a range. Right? And so we have our water to alkene reactor feed ratio here. What I want to do is I want to set our initial guess to that times the alkene flow rate, right? Which is E dot propylene F. And then it has a lowest possible of 0, and then we'll just say the highest possible is 2 times that ratio times propylene feed. Next, we have our distillation column, right? We have 6. We have our flow going in, our mole fraction in, distillate mole fraction, and our bottom with our bottom's mole fraction. So I'm going to type all of those out. So E dot D1 D E dot D1 dx or dy, sorry. E dot D1 B E dot D1 bx and E dot D1f E dot D1fx. Right. So going to look at flow first. So our flow going in, I want to use this as my initial guess, right? We're saying our initial guess is just going to be all the water going in, right? So then we have 0, or is going to be all the water that went into the reactor. We have 0 as our lower bound, and then our upper bound we will again say is 2 times this constraint. Oh, and we need to put in range here. And then for our distillate range, I'm going to say is about half of what went in goes out, right, as our initial guess. And then we want to say that our upper bound is this 2 times the constraint again. And then I will do the same for this this bottom. Now looking at our mole fractions, because we don't know what it is and it's an unknown value, we want to use comp instead of np.array. And so for this, I'm going to guess about 0.01 alkene, 0.03 ether, 0.06 alcohol, and a lot of water. And then through the bottom, going to have a very small amount of our alkene, some ether, some alcohol, mostly water. And this doesn't add up to 1, but it won't affect it that much. It doesn't really matter. And then for our distillate, we want our propylene. It's going to be, most of the propylene is distilled. And then for the rest of this, looking at this, our vapor liquid equilibrium, right, or equilibrium constant, we can see this, they're going to be about the same if we just do like a rough multiplication. So we're just going to get 0.33 for each of these. And now if we count up our unknowns, right, we have 4 unknowns from earlier, our 2 products, and our extent of reaction. Right, and then we have 1 more for our decanter water flow. That's 5 plus 4 plus 4 and plus 4. And that gives us 17 unknowns, which is the same number of equations we have. And so now I will go ahead and solve these equations. So enter that. So this comp needs brackets. And there we go. All right. Now what I want to do is I want to make this equations 2. And then for this root, right? So the root can't handle this many functions, right? So what we actually need to use here is this Jacobian, right? Our Jax that we imported, right? So Jax.Jacobian of our wrapped equations. And this actually has automatic differentiation, right? So that'll actually be able to use all 17 of our equations here, right? And that's actually also where this J and P comes in, and here in the concatenate. I think this actually needs an underscore here, right? So let's go with that. We have our X and then our X2 unknowns. And here we have our 4 from before, right? And you can see they are the same. And then we have all of our new ones here, right? So that totals out to 17. You can look at all of our here with X to named tuple, shows all of our variables, but and then our X to unknown is just the unknowns. And if we have constant dot as dict, that shows all of our known variables. All right. And that will be all for this video. Thank you.